Looking for projects for your academics? Need help with your project? Want any pre-built project? Then you are at right place. Welcome to my channel, Project Solutions Hub. Hey everyone, and welcome back to the channel. Are you a B.Tech CSE student looking for an impactful machine learning project that stands out? Today, we're diving deep into a real-world problem, credit card fraud detection. This isn't just about coding. It's about building systems that protect millions of people and billions of dollars. Let's get started. Credit card fraud is a massive issue globally. For your B.Tech CSE project, tackling this problem offers incredible learning opportunities. You'll work with real data, understand critical machine learning concepts, and build a system that has direct, tangible impact. It's a fantastic way to showcase your skills for internships and placements. Our goal is simple. Identify fraudulent transactions from a vast sea of legitimate ones. We'll be using a dataset from Kaggle. But here's the catch and the biggest challenge. Imbalanced datasets, fraudulent transactions, are extremely rare compared to legitimate ones. If our model just predicts legitimate all the time, it'll be 99.8% accurate, but utterly useless for detecting fraud. We need smart strategies to handle this. First things first, let's set up our environment. We'll be using Python, along with powerful libraries like Pandas for data handling, Scikit-learn for our models, and Matplotlib/Seaborn for visualizations. The very first step in our code is loading our credit card CSV dataset. Make sure you download this file from Kaggle and place it in the same folder as your Python script. When we run this, we immediately see the dataset's shape, indicating over 284,000 transactions and 31 features. And looking at the first few rows, we can see the anonymized transaction details. Once loaded, we perform exploratory data analysis, or EDA, to understand our data. We check for missing values, and thankfully, this dataset is clean. But the most critical part of EDA for this project is examining the class column. This is where we see the severe imbalance. This tells us that fraudulent transactions make up a tiny fraction, only about 0.17% of the entire dataset. To make this imbalance visually stark, we create a count plot. This imbalance is our primary challenge. Next, preprocessing. We separate our features, all columns except class, including time and amount, into X, and our target variable class into Y. We then split our data into training and testing sets. The key here is using stratify equals sign Y in our train_test_split function. This ensures that both our training and testing sets maintain the same tiny proportion of fraudulent transactions as the original dataset. If we didn't use this, our test set might not even have any fraud cases, leading to misleading results. After splitting, our output confirms the new shapes, and importantly, the training set still reflects the imbalance, Oversampled, value_counts, output to demonstrate the balanced classes. This is a critical step for tackling the data imbalance. Since fraud cases are so rare, our models might struggle to learn their patterns effectively. We use a technique called oversampling, specifically RandomOverSampler from the Imblearn library. What RandomOverSampler does is essentially duplicate random instances of the minority class, our fraudulent transactions, until it balances the class distribution in the training set. This dramatically increases the number of fraud examples the model sees during training, helping it learn the subtle patterns of fraudulent activity much better. Now the exciting part, model training. We'll start with the random forest classifier. It's a powerful ensemble learning method that builds multiple decision trees and merges their predictions. Notice we use our resampled data for training. We also include class weight equals balanced as an additional measure to give more importance to the minority class. After training, we make predictions on our original, unbalanced test set, Y original, because that reflects the real world we want to predict in. Let's look at the evaluation. The classification report is key. For the fraud class, we see precision of 0.89. This means when our model predicts a transaction is fraud, it's correct 89% of the time. Recall of 0.85. This is crucial. It means our model successfully identified 85% of all actual fraudulent transactions. We want this number to be high to minimize missed fraud. F1 score of 0.87. a balanced measure between precision and recall. Now, let's visualize this with the confusion matrix. True negatives, top left, approximately 85,281. Legitimate transactions correctly identified. Great. False positives, top right, 14. Legitimate transactions incorrectly flagged as fraud. These are false alarms. False negatives, bottom left, 22. This is critical. These are actual fraudulent transactions that our model missed. We want to minimize these. True positives, bottom right, 126. Actual fraudulent transactions that our model correctly identified. This gives us a clear picture of how well our model performs at catching fraud versus raising false alarms. Next, we try another powerful ensemble model, gradient boosting classifier. This model builds trees sequentially, with each new tree correcting the errors of the previous ones. We train it similarly on the resampled data. You'll notice its numbers might be slightly different. For example, in our simulated run, gradient boosting might have had slightly fewer false positives, but more false negatives than random forest. This highlights that different models offer different trade-offs, and choosing the best one often depends on your specific business needs. Finally, for imbalanced datasets, the precision recall curve and its area under the curve, AUCPR, are often more informative than other metrics. A higher AUCPR indicates better performance, especially when balancing precision and recall for the crucial minority class. We can compare our models directly using these curves. Our project is a solid start, but machine learning is an iterative process. Here are some key areas for further improvement, as highlighted in our detailed explanation. Feature scaling, more advanced resampling, hyperparameter tuning, other algorithms, anomaly detection algorithms, cross-validation, threshold tuning, feature engineering. So, there you have it. A comprehensive breakdown of a credit card fraud detection project, covering everything from data loading and critical imbalance handling to model training, evaluation, and future enhancements. This project not only teaches you core ML concepts, but also how to tackle real-world challenges with data. If you found this helpful, hit that like button, share it with your fellow CSE students, and subscribe for more project breakdowns. If you want the code, fill the form linked in the channel description. Happy coding, and see you in the next video. Thanks for watching. Keep learning with Project Solutions Hub, and don't forget to like, share, and subscribe.